Good afternoon. I'm Sharon Thomas with NERC. Thank you for joining us today for a webinar presentation on what space weather is and some of the science behind it. We'll hear about the potential ways that it can affect the grid, what measures can be taken to protect against these effects, and there will also be some discussion about reliability standards that are underway to help mitigate the risk. There are a few things that I need to mention before we get started. First, I need to mention that this webinar is being recorded, and by participating in it, you're consenting to being part of the webcast. The slides and the recording will be available on the NERC website within a few days at nerc.org/lab, and from there you can click on past meetings to find the recording. The webcast is being done as part of an award that NERC received from the Department of Energy, so we'd like to thank them for their continued support. During the webinar, we're going to have everyone on mute except for the presenters to manage background noise. And to ask questions, please use the questions function that's in the webinar software on the right-hand toolbar. And we'll have around 15 minutes at the end to take questions from the audience. So we have two experts with us today who will be sharing their insight on this topic. One of them is John Ostrich, who's a program manager of risks and hazards analysis at DOE. In this role, he identifies, prioritizes, and then manages a variety of projects addressing threats and hazards to electric as well as oil and gas energy systems. Recently, he's been leading DOE efforts to address geomagnetic disturbance and electromagnetic pulse events. He also represents DOE in interagency policy discussions on mitigation activities. John has a systems engineering background and has analyzed and managed a variety of projects related to energy assets and systems. He's worked for or supported DOE since 1992, and prior to that, he was an intelligence analyst with a focus on military systems in China and the USSR. We also have with us Mark Olson, who is a senior standards developer at NERC. He joined NERC in 2012 and has been involved with a variety of projects to develop reliability standards for transmission operations, physical security, and geomagnetic disturbance mitigation. Before joining NERC, Mark was a career officer in the U.S. Navy, where he served in positions related to the operations and management of surface ships and naval personnel. He has a master's degree in electrical engineering from the Naval Postgraduate School and a bachelor's degree from the U.S. Naval Academy. And with that, I will turn things over to you, John.
Okay, thanks. Can you hear me okay, Sharon?
Yes, I can hear you well.
Okay, great. All right, I'm going to go into the background first. That's going to take probably a little bit more than some of my other slides, so don't get concerned that I'm using too much time up because I think the background's good. Thanks for inviting me to speak on this topic. I think it's very important. We've been analyzing all threats and hazards to the electric grid for quite some time, and although the analysis is preliminary, I would say that space weather is one of the highest risks to the grid. We consider all things. Just give you a little bit of background on the sun and kind of how this comes about. So the sun is very volatile. You have solar flares, coronal mass ejections are actually visible if you look at it through a telescope. I've seen them myself on a very cheap telescope from Toys R Us. You can see with the filter, of course, you don't burn your eyes. A coronal mass ejection can actually cause a geomagnetic disturbance, which is what we're concerned about, and that's a major disturbance of the Earth's magnetosphere. So what the coronal mass ejection coming off the sun, and there's a picture of really a small one. If you actually look at the diameter of the sun, some of the larger ones actually shoot out from the sun, and they're as large as the whole diameter of the sun. They're just massive. And what it does is the magnetic field changes on the sun. It results in explosive projectile plasma. It's flung out to space. But it's not like light from the sun, which goes out in all directions at the speed of light, reaches Earth in 8 minutes. Coronal mass ejection typically goes in one direction, more like a shot from a cannon. And it goes much slower speed, only about 1 to 6 million miles per hour. Now, it seems pretty fast, but it doesn't reach here in 8 minutes. It might take half a day to 4 days to actually hit the Earth, if it hits it. And the majority of them actually miss Earth. If a coronal mass ejection does hit the Earth, it can change the geoelectric field on Earth, which can lead to what you'll hear people talk about GICs, geomagnetically induced currents, because of course current has to do with magnetism, and the Earth has a magnetic field. The sun throws magnetic field at the Earth, inducing current. That can travel through the Earth, along man-made structures. So it's not just transmission lines. Pipelines, rail lines also will pick up this current. And we're concerned about how the flows in the earth along these long transmission lines eventually flow into the neutral of a transformer. If that current goes in the transformer, and if it's large enough, it can potentially destabilize the grid, even to the point of collapse. It also could potentially damage the transformer. So that's why we're concerned about that. Now, just to talk quickly about the solar cycle, 11 years, and it's from a lot of peak activity, which you'll see in sunspots and solar flares, down to a solar minimum, which we're actually moving towards right now. The minimum was at 2008, and again, it'll be about 2019 will be a minimum. The cycle we're in, though, has been very, very weak, one of the weakest ones in the last 100 years. So don't think, well, I don't hear too much about storms. We really have had very few. It's extremely unusual, but actually, there's one going on right now, which is a very minor storm, and Sunday we actually had a moderate storm. And really looking at how they're labeled can be very confusing and kind of alarming as the media picks it up, because they're labeled a geomagnetic disturbance from G1, a minor, G2 is a moderate, G3 is a strong, G4 is a severe, and G5 is extreme. Well, it sounds like strong, severe, and extreme all sound kind of bad. And really, because we're having a minor one now, we had a moderate one on Sunday, and typically there's, nobody notices out in the general public. And even strong and severe storms, typically nobody notices. It's really the big worry we have is of those extreme storms, which happen about every 3 years. And the last one we actually had, though, was in October 2003. So, we haven't had one for a long time. Duration of these storms can be from a few hours to actually a day or two in terms of how long they last. And it's not a big pulse like an EMP from a weapon. It's long wavelengths that keep changing over time, over the day as it goes up and down. Some of the factors that actually may affect what kind of damage it can do to a transformer is really the design of the transformer. How old is it? How well it's been maintained? What kind of dissolved gases and water content does it have in it? The size of the transformer, larger, more impact to the loading on it. Of course, more loaded, more impact. And connection to long transmission lines. And typically, your larger transformers are connected to those longer lines. There's those ones that are most susceptible to this. Characteristics of that geomagnetic disturbance also is going to matter in terms of not just the size of it, but orientation of your system to the pulse and then how long it actually lasts. Other factors that come into play are the latitude you're at. More northerly is more susceptibility. Soil conductivity, which USGS looks at, if you're close to large bodies of water. Having a lot of reactive power reserves can help if you have a large one, and Mark may get into that a little bit. We need to go to slide number 3 now. And this really covers who's kind of looking at the sun. Of course, it's NASA does, and NOAA and the Space Weather Prediction Center looks at it and is watching for sunspots. Those are indicators of flares, which could actually end up creating these coronal mass ejections, which if you see them a few days out, power companies, independent system operators, get these warnings and can take some actions if they think it's if it's going to be a large one. The problem is if you understand magnets, even though we see it coming, we don't understand whether it's positive or negative or what angle it's going to hit at. And of course, 2 magnets, north and south hit, you have collision. 2 norths, you have it repels. So you have, and then you have all the things in between. So we really don't know what the orientation is, positive or negative in the angle, until it passes what's called the Discover satellite, which is brand new up in space, and we had an A satellite up there before. And you really have 20 to 45 minutes real specific warning from Space Weather Prediction Center of is this going to be a real big one, or is it, the orientation off, so it's not going to hit us. So you'll have a few days warning that something might happen. You'll have 20 to 40 minutes that, it's a miss or it actually is going to happen. So yeah, it's important to get those reports from the Space Weather Prediction Center. NERC gets them, DOE gets them, most utilities get them. If you don't, check out their website and try to set up the alerts so you're told in advance that things are happening, because you can take mitigation action to help configure your grid into a better defensive posture. USGS also collects data on magnetic field changes. These can be used to help predict and model your system and kind of what GICs may enter your transformers. DOE has a program to put these out. NASA has been doing that. Utilities have been doing that. Of course, USGS has those collection devices. It's less expensive than actually monitoring the currents. They're entering your transformer during a geomagnetic disturbance. We had a program that was supported with EPRI to put those out as well, monitors called GIC monitors on the transformers. That's even better than tracking the magnetic fields, but of course it costs about 10 times as much. And there are a large number of those around the country to really see what's actually happening to your transformer, amount of current that's coming in. All this data can be used to, like I said, to reconfigure your system to get into more protective mode. I think I'm going to turn it over now to Mark, and he's going to talk for a little while about what can happen to actually systems and things that NERC's doing. So Mark, why don't you take over?
Okay, thanks, John. Yeah, that's the right slide there. Yeah, thanks for inviting me to join today. My name's Mark Olson, and just to highlight, John and I work together on a number of initiatives to try to address this risk, and I'd say that NERC and the Department of Energy have a productive history when it comes to looking at severe GMD events. Back in 2010, following a technical conference that was co-led by the Department of Energy and NERC, we issued a joint report on high impact, low frequency event risk, and that included GMD, and there were an action plan out of that in many ways has gotten us to where we are today in addressing these risks. It should be evident from what John has indicated about the variability in GMD events that this is really a unique and challenging reliability risk. For one thing, severe GMD events, the very extreme ones, are relatively rare, particularly in comparison with our modern power grid. Historical storms like events that predate our grid, we don't have a lot of data on those, and so in many ways we're trying to evaluate what the potential impact is on the grid by making some projections about what those events might have looked like. Secondly, observing conditions of what extreme GMD events look like is very difficult. We can't place instruments on the sun, and the Earth orbits for where we do put our instruments are still a relatively long ways away from the sun. And so as a result, the science of these events is not perfect, and it's evolving. The geoelectric fields that are produced on the Earth by space weather is very complex, and it varies with the space weather interaction with our atmosphere. As John described, the way magnets interact is partially a source of variability. But we do know that higher latitudes generally have more problems than the lower latitudes do. We also know that more resistive ground structures generally have more problems with GMD events than lower resistive ground models. And there are other factors that exist. And then finally, what I really wanted to talk about was the power system itself. It's another variable in how GMD events will have an impact. The topology and how it's oriented around the storm affects the vulnerability. The length of the lines and their voltages in the power system affect vulnerability, and then the construction of individual equipment in the system. So consequently, NERC's effort has been to work with a broad group of researchers and industry experts and policymakers to advance the science and sound engineering approaches that can address these risks in an effective way and also at reasonable cost to give entities, utilities, options that that can be used. So we do know that the two primary risks to the grid are voltage collapse, and this occurs when the GIC currents that John talked about flowing in the transmission lines. When those and when they're in the transformer, they're creating reactive power drag on the system that can lead to this voltage collapse. There's also a production of harmonic currents that come from the transformer caused by the GIC flow in the neutral. That causes a phenomenon known as half-cycle saturation, which produces harmonic currents throughout the system. And these harmonic currents can cause relays and protected equipment to trip or operate in an unexpected manner. So both of those things can lead to voltage collapse. There's also the potential for equipment damage. The current flow in the transformer can, as it causes, it causes that additional reactive power demand, so the transformer is working harder, but also it can cause hotspot heating or circulating currents inside the transformer that will lead to very localized heating effects, and that can cause transformers to be damaged or reduce their lifespan. All of these conditions, though, are really dependent on a number of factors, like the design of the system, where it's located in the topology, and then the very GMD characteristics that the system is experiencing. So how do we know about this? Well, if you can go to the next slide. We know about these impacts really from some historical events and then some engineering study, but it's from the historical events in March 1989, the Quebec power system blacked out during a severe GMD event. And a little bit about that system. The Quebec power system is separate from our interconnection, so it's its own system. But it has some very long transmission lines that bring power down from hydro sources way up to the north. So they have some 1,000-kilometer transmission lines, and they're very high voltage, 735 kV voltage. So extremely high voltage lines that bring that power down into the metro area of Quebec. And in March 1989, a very strong GMD event happened that caused some of the reactive support equipment around that transmission line to trip very quickly after GMD conditions started, and that resulted in a large-scale blackout. Secondly, equipment damage was also noted during that storm, and this occurred here in the United States. Some generator step-up units in Salem, New Jersey. During the event, they experienced and it was observed that there was an increased reactive power demand, and there was measured dissolved gas increases, which is an indication that of the hotspot heating that might have been occurring inside the transformers there. And afterwards, after the event, the units were taken offline and examined, and they had damage inside that needed that resulted in them having to be replaced. So they were of a certain there were design factors involved, but it was an example of where geomagnetically induced currents caused a problem with transformers. So utilities have been looking at ways to mitigate these impacts, and if you go to the next slide, there are a mix of strategies that are available and in various stages, and all of these are evolving. And depending on the a number of factors. The effectiveness of the strategy or the appropriateness for a system can be determined. Operating procedures can prevent voltage collapse. The systems in advance of a storm can be postured into a more resilient arrangement that will reduce where the GICs are flowing, or maybe take certain parts of your system offline and reroute the power to avoid areas that are more vulnerable, or put you in the most resilient configuration that you can. Supporting operating procedures oftentimes involves using some monitoring, some GIC monitoring on the system to know where the GICs are flowing. That allows the operator to make better informed decisions. On the hardware approach also, there are equipment upgrades that can improve the resilience. For example, there are certain relay types that are less susceptible to GIC impacts than other types. And in the case of that March 1989 event, a situation like that where the relays cause tripping of reactive power support can be mitigated by understanding your relays and their susceptibility and making an upgrade there. There are also improved designs of transformers that are more resilient to GICs. And in cases now, there are many utilities, when they're replacing transformers, they're specifying certain GIC withstand capabilities and putting those into their procurement processes. There are some new technologies that can be used for reducing GIC flow in the transformer, or even blocking it altogether. Some of these are in their infancy. Generally, I would say this is a mitigation technique that's more in its infancy. There is some prototypes that a prototype that is installed, and some design efforts have been made with various utilities in North America. There's an extensive amount of planning and engineering that needs to go into the application of reduction devices. These devices are influencing the grounding systems, and the grounding systems are very important to the overall function of the power system. So a lot of considerations need to be made to ensure that those devices perform properly, but also don't cause any issues when there is no GMD event going on, that they don't interfere with the normal operation of the grid. Next slide. So I'd like to talk now about some of our reliability standards that we've recently put in place to support grid resilience and reliable operations in addressing this GMD risk. And as we've discussed, the variability of power systems and the technical aspects of the storms, the GMD events itself, I'll point out that the NERC standards are aimed at enabling entity-specific mitigation. They're not a one-size-fits-all solution to GMD risk. In 2013, FERC directed NERC to develop reliability standards and to follow two phases in that. The first was to develop and require our operating entities to develop procedures that can mitigate the risk. And those standards, those went into effect in April 2015. Again, the entities under that standard are required to develop operating procedures and to have procedures in place to receive the space weather information that John talked about, the monitoring that is being done at, for example, the NOAA Space Weather Prediction Center. So the procedures require our entities to be able to get that information and then to have procedures that have entity-specific steps that they would take to mitigate the storm. And so that standard is in place now. And the second standard is requires entities to complete detailed vulnerability assessments of risk to a severe GMD event, and then develop mitigation. And that standard was recently approved and is going into effect now, and I'll talk about that here in just a moment. Both of these standards apply to the extreme high voltage power system, 200 kV and above bulk electric system. The NERC planning standard, that TPL7, next slide please. This standard requires planning entities and asset owners to perform assessments and to develop corrective actions that will address the risks from a severe 1 in 100 year GMD event. The implementation for the standard will occur over a 5-year period with various steps in the planning process being phased in, and ultimately the corrective action plan, leading to corrective action plans and a completion of an end-to-end vulnerability assessment by the year 2022. Just a few comments about this standard. Part of the standard is this 1 in 100 year event. We refer to that as the benchmark GMD event. In developing the standard, we used a team of experts from the industry and some space weather experts to use collected magnetometer field or magnetic field data that has been collected over the past 30 years, and then from that develop this projection of what the most severe event in a 100-year period would look like. The standard requires entities to use the state-of-the-art modeling tools that are available to then use that storm and simulate the GIC flows that they would see on their system, and model how the system would respond to that. And then if the system were to not meet the performance requirements, if it were to lead to a voltage collapse, for example, then that entity would be required to develop a corrective action plan that would allow them to prevent that situation from happening. So that's a quick overview of the standard, and in your roles, you may be hearing about that one as entities begin putting the requirements of TPL7 into place. So with that, John is going to talk now about some protection approaches. John?
All right, thanks, Mark. And what I wanted to first do is kind of go over a few types of things that you may see, name group members over time as these assessments are done that Mark just talked about. Entities are going to be, putting together rate cases and trying to get cost recovery, except for some of these types of devices after they do their assessments. Who knows who's going to ask exactly for what. This is going to be based on assessments, but the kind of things that you may see is, monitoring devices, which is something that, Mark, you can probably talk about this a little bit later if you wanted. I think FERC directed NERC to, collect, magnetometer and GIC monitor data. So companies have those monitors out there. More of those are going in. Those don't protect the grid, but they do allow you to, model your system and see actually what happens to it to know, can I accept this risk or do I actually need to mitigate or to protect against it? So you may see companies asking for, rate recovery, cost recovery to put in magnetometers or variometers. That'd be measuring magnetic field data. You also may see folks asking for, they want to put in GIC monitors. That's, again, those are both monitoring, collecting data to help you model the system. In terms of protection, the things that could be put in would be actually GIC blockers. I'm going to talk about that a little bit and what the cost is. Series compensation can go on the power lines and actually block the quasi-DC currents from coming into the transformer as well. You can put different kind of grounding devices on your transformers, or you can design new transformers that just aren't susceptible to this. And, you know, somebody who has an old transformer might say, I want to put in this transformer, it costs a little bit more, but it's going to, you know, reduce or greatly the susceptibility to GIC, so that's possible. APP and Ramses Kerr just did a study a few years ago, which is published, and they looked at thousands of transformers and rated them on how susceptible they were based on the design, from you know, highly susceptible to not susceptible at all, and no transformers had no susceptibility. There were about 70 of the several thousand that had very low susceptibility. So most transformers out there are susceptible to this, and a lot of them may not be based on location, which is good. But in terms of design, there's some really great designs out there, and there's very few of those designs, you know, in place. So in terms of blockers, I also wanted to comment a couple things. One thing that you had said, Mark, about back on your slide 6. If you could back up to slide 6 just for a second. Can we back up? Okay, your first bullet there, operating procedures can prevent voltage collapse. And you're right, you explained it. I just want to make it clear to people that he does have the word can there, it's not will. Operating procedures, if that's all everybody did, if you have the extreme, you know, storm, the 100-year storm, NERC and DOE both feel, and most utilities, you know, you're going to have a major voltage collapse right now until, you know, these protection and mitigation procedures are put in. And mitigation alone probably isn't going to do it by itself. So you might be thinking, well, why does somebody actually have to protect the grid? Can't they just mitigate this problem away? Probably not. You know, in some cases you can, but the 100-year storm, probably not. If you disagree with Mark, you can jump in, but I think we agree on that we're probably going to have to go beyond just mitigation, right?
Yeah, this is Mark. I think it's very right that a mix of things is probably needed. You know, we work closely with our Canadian counterparts. NERC is a North, you know, we have North American jurisdiction, and it is a mix of approaches. Operating procedures are pretty advanced and in many entities in the Canadian areas, and they usually involve that mix of having monitoring and operating procedures. So your monitoring fed into the operator and a thorough knowledge of what the system would do is what triggers, you know, informed actions. But also these entities have done much to upgrade equipment, relays, for example, or specifying those transformers which have GIC withstand capabilities. So I think you'd see that a mix of hardware and operating approaches is probably where you would end up for the severe event, and it takes study to know what the effective way to approach it is, I think.
No, thanks, Mark. I absolutely agree. I just wanted to make sure that was clear so somebody didn't zone in on that one, saying, "Oh, well, we maybe no protections needed." We, you know, after the assessments are done, our hypothesis on both NERC and DOE is that there's going to need to be some protection, right? That operational procedures can do a lot, but it's not going to be enough in the extreme cases. So, right, you can zoom back to my slide. I think was slide 9. Okay, on protection. So a GIC blocker is certainly one way to protect, because what happens is this current goes into the transformer, and Mark kind of went over the different things it can do. It could cause voltage collapse, it can cause overheating the transformer. You can just block that current from coming in through the neutral. And the GIC blockers on the market today is basically like a capacitor, which blocks the current from coming in. Those are not inexpensive. You know, some of the slides from one of the vendors said like $125,000. I just saw a recent study that they put out looking at protecting all of BPA, and it really came out to, I think their estimate was about $900,000 per substation, assuming you protect about two transformers per substation. So, the blocker may be 450,000. So that's not insignificant. If a transformer costs $2 to $7 million for some of the large power transformers, that's a big chunk of change. Spending almost $500,000 to protect one, and that includes hardware installation, software, all those things. The hardware itself doesn't cost that much, but it's quite a bit of money. So you're probably going to be protecting, critical substations and ones most susceptible. So that's one possibility. There's only one out there right now. ATC has one deployed. It's working. I mean, I've seen some of the data on it, and it seems to be blocking the current, but there's only one out because no one really was required to put them out. It's kind of expensive. After doing assessments, I expect we'll see some more of those go in. Series compensation is another way, actually on the power line, as opposed to blocking it from coming into the transformer. At the transformer neutral, you can put the capacitors on the power lines to prevent the DC current from flowing through. Series compensation on power lines is typical in a lot of the western part of the country. It's not to block space weather impacts. It's to let your power lines work more efficiently and allow yourself to move more voltage across that line so you don't have to build another power line. And so it's a lot cheaper. Some estimates have said series compensation might cost 1/3 the cost of putting a new power line, and some say 1/10. So instead of building a new power line, putting those in to bump your voltage up is a great thing, and it does give you the benefit of protecting against those induced currents from geomagnetic disturbance. Problem is the cost is much higher than the blocker. It might be 5 to 25 times. A lot of data out there, so who knows exactly, but more than actually just protecting with a blocker. So it doesn't make a whole lot of sense to say I want to put series compensation in as a space weather protection measure. But it gives you that protection if there's other reasons to put it in. Like I said, it's typical in Western utilities. A lot of it's going into Texas right now because they're putting a lot of new power lines in to connect to all of the new wind that they're putting in. And they're putting series compensation on those lines, not to block space weather, for efficiency of the lines and other reasons. But it's giving you that protection. So as you do assessments to say where I might need to put a blocker, if it's already blocked from these various lines, those are just things that have to be taken into consideration. Fortunately, it's not very common on the eastern grid, which is where quite a bit of the power lines are and quite a bit of the substations. Very little series compensation in the east. They do create other problems. What doesn't? And I'm not going to get into all the details of exactly what it does, but I'll throw it out there. It does cause problems with zoned impedance protection schemes, but I'm not going to get into what that is. Let's see what else. Okay, another thing you can do is put static or active grounding devices from the transformer neutral to ground connection. You also, as I said, you could, as you put new transformers in, ask the manufacturers to build them with high GIC withstands. Those two exist. The delta connected transformer windings, less susceptible. Again, very few have been ordered that way because people weren't worried about that. So as you replace old transformers, it's legitimate to think about building in your withstand as opposed to, attaching a protective device to it. And as Mark also mentioned, adjusting protective device settings is important to prevent voltage collapse. Hydro 1 up in Canada collapsed because a lot of things tripped offline. Because their settings were set to protect the system. They didn't have it set to survive through a GMD storm. If they had adjusted some of those settings, which they have now, it might have been a different case if you have a storm like that again. They've done a lot of work since 1989 to try to prevent that from happening again. Other potential protection, is have smaller transformers, less long distance power lines, more distributed generation, things that, we're looking at Department of Energy, smaller grids, being closer to where your power generation is. Smaller transformers do reduce your susceptibility. That's a long-term strategy, though, not necessarily a protection scheme you do just to do that. There's a lot of other things people are looking at. What if you underground transmission lines? You know, we've undergrounded distribution lines. What would that do? There's some folks starting to look at that. I don't have any data on that yet because that study hasn't started. Let's see. I think that's all I wanted to say about protection, some of the costs. Let's go to the next slide, and I'll talk a little bit about what we've done the last few years on this, and I'm going to turn it back to Mark. We'll talk and wrap up about what NERC has been done, and then we'll open it for questions. So DOE, in the past really 4 or 5 years since I've jumped in and started working on it, I've been working on it since about 2012 or 13, got involved in the Sunburst program with EPRI, and that was to put out GIC monitors. So again, this doesn't protect, but it does let you know what the current is coming into your transformer in real time, and you can take measures to reduce the loading on the transformer if it's overheating, potentially try to drop the transformer because you don't want to have system damage. So there were 10 when we got involved in the project back in about 2013-14. On the Eastern grid, we now have over 40 to 50 in all 3 major grids, ERCOT in Texas, and the Eastern and Western grid. We also lately have been putting in variometers, which are inexpensive magnetometers, so we can measure magnetic field changes as we have small and medium storms. So again, utilities can look at that data, combine it with the magnetometer data from USGS and NASA and their own data to try to model their system to see where they might have susceptibility. So we've been putting some of those in. Our plan is to get 12 in really by the end of this year from 0. We also just completed a monitoring plan for geomagnetic disturbances. Idaho National Lab did that for us. It isn't published yet, will be in the next few months. It really goes into what kinds of things would you like to collect to better be able to assess your system. What do you want to see happening during a geomagnetic disturbance storm, such as what's the hot spots in my transformer, what's the heat of them, what's happening to my oil, what kind of currents going into my transformers, things like that. We also just funded a study with Oak Ridge. They looked at susceptibility of the Eastern grid, got into pretty detailed information on various transformers. So that wasn't published because it's kind of sensitive. Certainly can share with people who have a need to know that. There was an earlier Western study done by Pacific Northwest Lab that is published. Didn't get into as much detail. We also did an assessment of the GMD benchmark event. It's called Review of the GMD Benchmark Event in TPL-007-1. That is online. You can find that. Bottom line on that is we had Los Alamos look at the GMD benchmark NERC put out. We thought it was a little bit low and really needed to be continually assessed. And I know NERC is doing that and doing some work right now to look at that. I think the benchmark event was 8 volts per kilometer at 60 degrees latitude, and I think we thought it should be 13, something like that. So, but we also agreed that the standard as it was made sense to go out and just needs to continue to be assessed as the science changed. We also are testing transformers. We have a program called Transformer Resilience Advanced Components, $5 million program. 4 awards have been made in the past year, and each of those awards is having various entities and companies do new transformer designs to be not just for susceptibility to GMD or EMP, but just in terms of efficiency and also more modular, smaller, so you can move them quicker. And if you happen to lose some transformers, we also just published a study required by the FAST Act called Strategic Transformer Reserve. This was a report to Congress issued March 2017. That's also online. That goes into our recommendation on what industry should do in terms of having spare transformers or what kind of reserve should be set up. So if you lose several, that we can quickly get those replaced, or the industry can. We also have in the works a pilot program to actually put protection devices on the grid. Don't know exactly how many there'll be, probably a handful. We're actually working with FERC and with NERC to try to, they're going to help us work, and you folks are helping us work on, cost recovery strategies for how, how you can put those in and actually get those paid for. A couple other things to say, and then I'll pass it back over to Mark, is, besides just these various things we're doing on protection, there's also, some looks at what you can do to mitigate as well. I mentioned instrumentation of transformers. It's really important to see if a problem's, quote, brewing in your transformers, so you can take action to prevent damage. Some of that really needs to be done as the transformer is built and designed. It's hard to go in and put an instrument inside your transformer to start measuring things if you've already built it. Other things that could be considered, as Mark said, reconfiguring your grid. You may have to disconnect some things if they're overheating, so you don't have the damage to them. Load shedding may have to happen, and that's certainly a bad thing. But if your grid's collapsing, you want to have parts of it shut down in a controlled, intelligent way rather than having a collapse. I think that's all I wanted to cover. I'm going to turn it back over to Mark, and he's going to talk about some NERC current activities and initiatives, and then we'll take questions. So Mark, back to you.
Thanks, John. I'll just cover this quickly so that we can open up for any questions. But some of our focused ongoing work is to support the implementation of the standards. There's a good deal of training and information sharing that we believe should be done. It is a North America-wide standard, and so what is well understood in our Midwest entities or utilities is less understood, guaranteed, in Florida and Texas. So we have some information sharing efforts that we're doing, and we're also improving the tools that the industry has to work with. We work with vendors through a GMD task force that is NERC sponsored and led to make sure the feedback loop is there from the industry to the vendor community that develops the software tools that the industry needs to carry out the work here. We are working on some revisions to TPL7 that would address FERC directives. One area is with the benchmark GMD event. In approving our standard, the Commission approved our benchmark event, but also directed that we try to look at localized impacts that could happen from a severe GMD event. So we're developing another GMD event that will be used in assessments. We also will be putting specific deadlines for completing mitigation actions in a future revision to the standard, and we'll be requiring entities to obtain GIC data that they'll use for validation and awareness. So those revisions are in development, and NERC and the industry will use our stakeholder process to develop that standard, the second version of TPL7, and we'll be filing that by May of next year, which is our deadline. There's some additional research topics that FERC wants us to look into, and we have a work plan that we have developed with our association at EPRI, and also part of that, EPRI will also work with some of our national labs and other researchers to help us meet our research goals that came out of the FERC order. So I'll leave it at that and leave some time for any questions that you might have. We've certainly put a lot of information out and done a lot of talking, so invite your questions now for John or I.
So if you have questions, if you could type them into the questions box on the GoToWebinar toolbar on the right-hand side of your screen. I'll read them aloud to the presenters, and they can answer your questions. So.
Okay, thanks.
I have one question to start. I was wondering if you have any information on how likely it is that space weather events could shut down parts of the grid compared to other threats that are out there.
Mark, do you want to start or do you want me to start?
I'll say something first. I don't think we have a comparison necessarily of likelihood there. NERC has, we prioritize risks through a process that involves a variety of stakeholders, and every year NERC produces a risk matrix and a prioritization scheme to focus our efforts. And GMD events are always in that prioritization. They're something that we believe is important to address, but I don't have an answer for a relative comparison of different types of risk.
Yeah, this is John. I would think that, looking at natural events, it's one that, can be continental in scope, a geomagnetic disturbance event. That's why we're concerned about it. I don't know if there's any other natural event that could really do that. I mean, a catastrophic earthquake, say along New Madrid or Cascadia or San Andreas Fault, could certainly cause a lot of damage and could cause regional outages. But, there's probably nothing occurring naturally that could cause the type of widespread outages I think a geomagnetic disturbance could, but it really has to be that 100-year storm. The 10 or 20-year storm's not going to do that. Adversarial attacks certainly could if they, attacked all the right things in a coordinated way. That's hard. We're not going to tell anybody how they could, because you don't want to tell bad people how they can do things. But, if people had a coordinated physical or cyber attack, that's certainly something we worry about too. If enough things went down, it could be a really bad day.
Thank you. The next is there a location to find past storm information, and where can you find information on developing storms? You mentioned like the NOAA website, for someone at a commission to find that information out. What are the sources that they can turn to?
I think you go ahead, Mark.
Well, I would recommend one bit of reading is the 2012 GMD report that NERC published, because it does summarize a number of historical events, and it lists some other resources that you could go to. So that's available on the NERC website. I'd be happy to point someone to it more directly, but it's the 2012 GMD report, or it was also called the 2012 GMD interim report. And then the NOAA Space Weather Prediction Center is a site that has a number of educational resources, and also provides the current this is a manned 24/7 facility that is watching the sun and taking the inputs from the satellite monitoring that John talked about, and other feeds, so that that's available on the internet. It's the Space Weather Prediction Center.
Okay. Great, thank you.
I don't think I have anything to add to that. I think, looking at NERC's reports a good idea. Like you said, SWPC, Space Weather Prediction Center, will have information. Hard to find what all those storms are. I mean, there's a few other websites that have them out there, but I think it's best to look at something like a NERC or the Space Weather Prediction Center to get, really the official numbers on what those were.
Okay. The next question is, has NERC and DOE worked with the FCC to ensure cellular communications are operational during these events?
I can answer that first, and then you can answer, Mark, if you want. I don't know that we have worked with the FCC, not that I know of. I do know, and that's a good point, space weather has multiple impacts across various sectors. There's GPS satellites will be disrupted. High-frequency communications will be disrupted. Communications is certainly important to the industry. It's not, our sector. The communications folks look at that, and satellite folks, and there's problems with transportation, aircraft, radiation to people in airplanes. Those get rerouted. So there are a lot of impacts. There certainly are impacts to communications. I'm aware of them, but I haven't really looked at those, other than I know that I am on a White House directed space weather task force, and there's all sorts of agencies are on there, and everybody's looking at their little piece of it. So there are folks looking at the communication side and very concerned about that. I'm focused more on the grid as opposed to communications, but I don't know, Mark, you want to add anything to that?
I would just add, I guess, that I think we recognize it as a cross-sector risk, and it's the type of thing that does have visibility through the Electricity Subsector Coordinating Council, which works with those other subsector councils. I know that some initiatives through the Space Weather Action Plan involving DHS would involve the different sectors trying to look at scenarios and how the different subsectors are affected. So it does get attention, and it's recognized that at least the power delivery to the communications system is something that's looked at and is part of the ongoing risk analysis being done, I think, in our country.
Well, let me add one thing to that too. I'm not involved in it, but the Department of Energy with Homeland Security, Intelligence Community, and DOD does have a work group. Those core agencies do look at areas that are of significance to all of them, and space defense and space weather is certainly a threat to satellites. So there is a group that's looked at that. Again, that's not something that's publicly available and what all the threats are and defenses, but it is a concern of the country that's been looked at. So I'll just add that, but there's not much else I can say about that.
Thank you. We have one more question. You mentioned GMD standards that apply to 200 kV and up. Do the broad effects of GMD mean that protection for distribution is just as important? Would analogous protections for operational and technical things help distribution?
There's actually some technical justification for using 200 kV and up, and the higher voltage systems are more susceptible to GIC due to the resistance in the transmission lines, and also the likelihood that those transmission lines are much longer. So there's a technical foundation to the 200 kV and up value. Going forward, as entities begin to model their systems, there are some entities that are bringing in the 100 kV into the models. I think we'll learn more about that and the importance of doing that, but the 200 kV criteria in the standard is really based on a technical justification, and distribution systems have a less susceptibility to GIC.
Okay, thank you. We are just about out of time, so thank you, John and Mark, for your very informative presentations. That was a great overview of the origin and effects of space weather on the grid, as well as mitigation measures, and also current and forthcoming standards to protect electric infrastructure assets. So with that, I will conclude the webinar, and I hope you all have a great afternoon. Thank you so much.
Thank you very much. Pleasure. Bye.
Thank you.